All right. Oh, I never set the...
I apologize for being late.
I apologize. I apologize for nothing. Let's see here. That seems relevant. Let's get... A wizard is never late. Oh, yes. Yeah, well, I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for this day again. I thank you for this class and this time we have to meet and study your creation. Just pray that you be glorified in what we do. Help us to not get confused today, Lord. In my prayer, Lord Jesus, amen. I always feel like I need to pray that when I'm talking about quotient spaces because it is a weakness of mine, for sure. Okay, but let's get to it. So last time we talked a little bit about some constructions that are quotient space based, like we talked about the wedge sum. So like last time, for example, the wedge sum of two lines is this, right? So it's also sometimes called the 1-point union because you're just gluing them together at one point, right? Or the wedge sum of two circles, the so-called figure 8 space. So you're just gluing the two circles together at one point. Something that occurred to me, the zero divisors in an algebra are a wedge sum, at least in my experience. Like for the hyperbolic numbers, this is the real axis and the imaginary, the J-imaginary axis. It's not really a thing. But, the zero divisors are the lines y equals, this is the zero divisors of H. They're the span of 1 plus J, wedge sum with the span, the other wedge, wasn't it? This wedge. Wedge spun with the span of 1 minus J, I believe. You multiply that times that, you get 0, and yet they're not 0. These are the zero divisors of the, hyperbolic numbers. Things of the form z equals to x plus jy such that, j squared is equal to 1. And I think it's actually kind of interesting, H3, which is the 3 hyperbolic numbers. It's also the real group algebra of like z mod 3. Anyway, so it's things of the form, let's say, zeta, let me try that again, eta equal to x plus jy plus j squared z, and j cubed equals to 1. So technically speaking, it's the real group algebra of the cyclic group of order 3, if you like. If you study this thing, the zero divisors of H3, it turns out they're I'm trying to think of a good way to, let me just say it geometrically. It's the plane with normal 1, 1, 1, wedge summed with the normal line to the plane. So like, if I was to foolishly attempt a picture of this, here's the zero divisors are like that. There's like a plane of them, and that line normal to the plane, the wedge sum of those two things is actually the zero divisors of H3. I don't know, I just think it's interesting. So, as a means of description. And so exercise 3.55, which I'll probably assign to you guys, says show that every wedge sum of Hausdorff spaces is Hausdorff. We talked about that a little bit last time. Let me read this paragraph. I think it's worth reading. Unlike subspaces and product spaces, quotient spaces do not behave well with respect to most topological properties. In particular, none of the defining properties of manifolds, locally Euclidean, Hausdorff, second countable, are automatically inherited by quotient spaces. In the problems, you'll see how to construct a quotient space of a manifold that's locally Euclidean, second countable but not Hausdorff, and also one that's Hausdorff and second countable but not locally Euclidean, and one that's not even first countable. So basically there's lots of ways that the quotient space construction break the structure of a manifold, all right? So you have to be careful with quotient spaces in manifold theory. But we do have this proposition, which I will not prove, but I will state, and here it is. proposition 3.56, it says suppose P is second countable space and M is a quotient space of P, period, if M is locally Euclidean, then it is second countable. All right. Thus, if M is locally Euclidean and Hausdorff, then it's a manifold. So do you guys have any questions about this? I mean, the proof is given on page 68 of this book I'm using at the moment. So we're using Introduction to Topological Manifolds. I'm just really covering a section in it, more or less. This book here by John M. Lee, second edition. It's a wonderful book. So the locally Euclidean means that there exists, homeomorphisms to open subsets of Euclidean space at each neighborhood of the manifold. So there's like a one-to-one bijection with Rn, at least locally. That's what locally Euclidean means. Second countable is a more technical topological thing, but it has to do with basis of neighborhoods for the space. Hausdorff means you can separate points. So like a manifold, a topological manifold, is a space which is locally Euclidean, second countable, and Hausdorff. All right, those are the terms and conditions for a topological manifold, which it turns out is, that's a lot. Anyway, so yeah. So he says typically to prove a given space is Hausdorff, you have to work from the definition of Hausdorff. However, for open quotient maps, we have the following criteria. So this is proposition 3.57, 57 rather. And here it is. Suppose Q x goes to y is an open quotient map, then y is Hausdorff if and only if the set R equal to x1, x2 such that q of x1 equals to q of x2 is closed in the Cartesian product of x with x. All right. Let's look at the proof of this, because I think the proof may just help bring some of these terms to life more. And I'm probably going to regret doing this, but let's try. So, all right.
Find out.
We'll find out soon, huh? So let us suppose that y is Hausdorff. So we're going to suppose we have an open quotient map, and suppose I'll follow the proof anyway. He says suppose assume y is Hausdorff. All right. If x1, x2 is not an element of the set R defined above, then there exist disjoint neighborhoods V1 of Q1 of x1 and V2 of Q of x2. Hence, the inverse image under Q of V1, Cartesian product, the inverse image under Q of V2 is a neighborhood of x1, x2 that is disjoint from R. Does that make sense? So if x1, x2 is not an element of R, that means that Q1 is not equal, Q of x1 is not equal to Q of x2, right? But those are two separate points in Y. They're distinct points in Y. If Y is Hausdorff, then of course there exist neighborhoods which separate the points, right? Since Q is a quotient map, it's continuous, right? So we have an open set cross an open set. I mean, this is certainly a subset of x cross x, which is open, and it contains the point x1, x2.
And x1, x2, not R, was arbitrary. It's too early to say this thing.
You think x1, x, so it's an arbitrary, so you say this shows that, so what you're saying is then the complement of what? So if we take x cross x, right, and we remove R from it, is what? What does this argument show? We've shown that an arbitrary point in that the x cross x complement by R is an interior point, right? So this is open, yeah. So therefore, what can we say about R? Remember our definition? Yeah? What do you say? It's closed, right? Because if the complement's open, then the set is closed. So that is what part of this proof? It's the forward proof part, right? How about the reverse then? Can we do that? I mean, this is why I like using John Lee's books, is because usually if I just try to, open it up and try to understand the proof, it usually works out. All right, so conversely, assume R is closed. Right? Then let y1 and y2 be elements of y with y1 not equal to y2, right? So pick distinct points in y. And we can select x1, x2, and x such that what? Q of x sub I equals to y sub I, right? Why can I do that? I mean, isn't that assuming that Q is surjective?
Is that required of the quotient map?
It is required of the quotient map. So we know that the quotient map is surjective, so that's reasonable. And note that x1, x2, so my question to you is this point, x1, x2, is it in R or not? What do you think? pair x1, x2, is q of x1 equal to q of x2? That's the condition to be in R, right? But q of x1 is not equal to q of x2 by construction here, right? So this is not an element of R, right? Therefore, it's in the complement, which means what? He says that means that there exists a product neighborhood. So here we're getting into the weeds a bit about topology, but for a product topology, this is what's available to you. A product neighborhood, U1 cross U2 of x1, x2, and x cross x, disjoint from R, since Q is open, I'll tell in a second. Since Q is open, Q of U1 and Q of U2 are open disjoint neighborhoods of y1 and y2. So to say a map is open is to say that it maps open sets to open sets. To say a map is closed means that it maps closed sets to closed sets. So what's the difference between like continuous and open? A continuous map is one that the inverse image of an open set is open, right? It maps in that way. But there's no guarantee that a continuous map is an open map. Like you can have maps which are continuous but not open. I think open maps are necessarily continuous, though, if I remember right. Sounds like a good homework problem. So that completes the proof there, right? And then there's a corollary. So corollary. 3.58. Yeah, suppose squiggle is an equivalence relation on space X if map X maps to the X mod the equivalence is an open map. And that's the natural map, right? That's just the map to the set. You take a point to its equivalence class, right? If that's an open map, then X mod squiggle is Hausdorff. If and only if squiggle is a closed subset of X cross X. Remember, we can look at an equivalence relation as a subset of the Cartesian product of the set with itself. All right? So, okay, so great, let's move on here. So the first section in here, which I've taken my sweet time to cover, gives us a bunch of examples of quotient spaces, right? But now we're going to change perspective in the next subsection here, and we start to ask the question of when is a known space actually a quotient space, all right? In other words, if X and Y are both topological spaces, we're going to explore conditions under which the map Q going from X to Y is a quotient map. So I'll state the question. Given Q, a mapping from topological space X to topological space Y, is Q a quotient map? Right? The question that we then followed up this question with last class was, or is it too late? Is it too late to topologize? So it's the natural question to ask here. That was the joke from last class. But it needs some setup. I devoted 20 minutes of class to a totally bogus example, just for the purpose of saying those words. But it turned out to be a good pedagogical device to introduce about a half a dozen topological concepts. So I have no regrets. So the definition. Any subset of the form Q inverse of, and so maybe it's helpful to put some brackets here. These brackets are not always given because here Y is a single element. For some is called a fiber of Q. Now this is not special to this discussion, all right? Any subset, I mean, you can talk about fibers for any map, all right? And probably, in my estimation, one of the most important concepts of equivalence is the fiber equivalence, right? Like, if you just, example, so comment. Forget about the quotient spaces for a second here. If I just have a mapping from, a set A to a set B, right? And here's A, and here's B, right? And suppose I want to make that mapping into a bijection, right? How can I do it? Well, if I want to take this and elevate it to a bijection, there's a fairly easy thing to do in terms of how do you make it onto? Well, that's kind of stupid. You can just replace this with F going from what? From like A to just change B out for F of A, right? Right? So there you go. Now it's onto. Wonderful. Right? And then if you start picking points in here, right? And looking at what those, they go to particular, if this is Y1, Y2, Y3, well, there's an inverse image that those go to in the domain. And if you look at that, like what's F inverse of Y1 intersected with F inverse of Y2? What can you say about the intersection of two fibers, supposing Y1 is not equal to Y2? What does this look like? You're looking for X in A such that what? F of X equals to Y1 and F of X equals to Y2. Those are hard to find, right? Like there's none of them. So this is empty. So the fibers are disjoint, and as such they partition the domain. But any partition of non-empty, any partition of a set like that corresponds to an equivalence relation, right? The equivalence relation is simply that 2 points in A are equivalent if they're on the same fiber. All right? So if your domain for this mapping we're thinking about constructing, right, if your domain contains more than one fiber, more than one point on a fiber, it's hopeless for that mapping we're constructing to be bijective, right? You can't form an inverse if you don't have one-to-one. And if I take more than 1 point from each one of those fibers, short of some kind of chicanery, you know. So if I just want to, so one way I can do it is I can use the axiom of choice, and I can select what's called a cross-section, S, and then F restricted to the cross-section, right? Where the cross-section I'm saying is you're just picking 1 point from each fiber, right? I can do that by the axiom of choice. So if I select a cross-section and I trade out my domain for the cross-section, then I've got a bijection. And this is a completely general construction on how to create a bijection from a function.
Could you also just say define a new function f that goes from equivalence classes, and it wouldn't be the axiom of choice to do it?
Well, yeah, alternatively, like you said, let's say G as a mapping from what? A mod the equivalence to f of A, just like you said, right?
Not that it makes any substantial difference, but that wouldn't require the axiom of choice, right?
I guess not. I don't think that's an interesting point. It doesn't require, I don't think it requires the axiom of choice. Devil's in the details, of course, but the axiom of choice does nevertheless give me a representative of each equivalence class. See, that's all that's going on here is like G of bracket X, right, is equal to F of bracket X intersect the cross section. That would be the relation between these constructions. We do this in all kinds of math classes. We do this in group theory, we do this in linear algebra. Like, if any time you're looking to elevate something to a bijection and you want to get injectivity, you have to deal with this issue. And there really is two different ways to do it. The one is to keep the objects that you're already working with, points, right? If you do that, then you need to throw away everything in the fibers except for one, right? But then the other thing to do is just to squash all the fibers to a point. That's the quotient space idea. It's like, you guys at abstract algebra, you're talking about factor groups. That's pretty much the same thing, right? If you have a homomorphism, if you have like a homomorphism, if you have a homomorphism, say phi, from a group G to another group H, right? If you take G mod the kernel of phi and let it go to, say, phi of G, right? And you define this by the natural property, namely that, we call this thing phi bar. And you define phi bar of, like a kernel phi to simply be equal to phi of A. Well, then phi bar is an isomorphism. This is the first isomorphism theorem of group theory. It's also essentially the first isomorphism theorem of linear algebra, except in linear algebra we don't use multiplicative cosets, we use additive cosets, so it looks a little different. But it's the same idea, and it's exactly this issue. So it just so happens that both in group theory and linear algebra, the size of the fibers are uniquely related to what happens at the identity. That doesn't have to happen other places. Other places, the size of the fibers can be really radically different at different places in the domain of your map. You could have some fibers zero-dimensional, some fibers one-dimensional. There could be all kinds of variety in the fibers. So, like, actually, it may not actually be plausible to. I mean, the axiom of choice says that there exists a cross-section, right? Can you actually write one down? Constructively? Well, that's another matter, which is why we sometimes get squeamish when we have arguments that use the axioms of choice, because it's one thing to have a proof of something existing, it's another thing to have a construction. All right, go on here. Okay, so further part of the definition here. U, a subset of X, is saturated with respect to Q if U is equal to the inverse image of some set V for some V subset of Y, all right? So here, again, it's the same setup, right? Q goes from X to Y. Okay, guys? So then I'll probably assign you guys exercise 3.59. It says, you know, for Q any map from X to Y, U is subset of X, show the following are equivalent. U is saturated. U is equal to, look at this. I love part B. U is equal to Q inverse of Q of U. All right. It's like, how could that not be true, right? Well, yeah, think about that. Part C, U is a union of fibers, right? It's a union of fibers. And part D, let me just put down part D, exercise 3.59. Part D, you're asked to prove that U being saturated also means that if X is an element of U, then every point X prime in U, not U, every point X prime in X, rather, such that Q of X is equal to Q of X prime is also in U. Let me put that more specifically. X prime is in U is what he's saying, okay? That construction of also, if I'm sleepy or tired, I mean, I don't do well with sentences that use this also construction, personally. It's an allowed grammatical construction, but to be, X prime's in U. Okay, so, yeah. All right. In other words, part D is again saying almost the same thing as part C, which is if you've got part of a fiber, you have to have all of the fiber. You know, that's the way I could read part D. Proposition 3.60 says the following: a continuous surjective map Q from X to Y is a quotient map if and only if it takes saturated open sets to open subsets, or saturated closed subsets to closed subsets. The good news for me is that I don't have to prove this, because you get to. Yes?
Is there a reason why the first time you write the sets, it doesn't say
Good question. I don't think so. Everything's subsets here. Sorry, I missed a sub. All right. Move along here. So proposition 3.62 has some properties of quotient maps. So part A, composition of quotient maps is quotient map. B, an injective quotient map is a homeomorphism. C, if Q is a mapping from X to Y, is a quotient map. I regret writing this out. And U subset of X is saturated. Oh man, I'm sorry, I skipped the D. What's wrong with me? Q is a quotient map. Oh, my stupid eyes just jumped the line. Rats. QXY is a quotient map, comma, dummy, a subset K of Y is closed if and only if the inverse image of K under Q is closed in X. All right, D, if Q is a quotient map and U, a subset of X, is saturated, open, or closed subset, then Q restricted to U, which is a mapping, understood to be a mapping from U to Q of U, okay? So that, I mean, to be fussy, sometimes I would say that's not. This is an obnoxious thing about restrictions, is like, sometimes you want a restriction where you're not modifying the codomain. Other times you want a restriction where you swap out the codomain for something different, right? So this time I'm swapping out the codomain for the image of U, and I'm defining that to be this. All right. Anyway, then that is what? Is a quotient map. And finally, E, which says if you have an indexed family of quotient maps, an indexed family of quotient maps. So if you have an index family of maps, so I got Q alpha going from X alpha to Y alpha. For each alpha, a quotient map, all right? Whole family of these things. All right. Then if you take Q and define the mapping on the disjoint union over alpha of the X alpha, mapping to the disjoint union over alpha of the Y alpha, guess what? Is a quotient map where Q restricted to X alpha is what? It's equal to Q alpha, okay? So that's how we're building the Q. And that seems reasonable enough because the disjoint union has points that are, you know, in the sets which are being disjoint unioned. So, all right, yowzers. So the good news is I don't have to prove it. The bad news is you might have to. But I actually don't think that these are probably hard. I mean, I think these exercises actually, doing these exercises will make you understand the section more deeply. You know, so it's probably worth assigning some of this. I don't see the danger in me assigning all these is if I assign so many that like you just feel like you're doing the same thing in multiple exercises, then I haven't achieved my goal, right? If they're boring. But if you're still, like the exercises are, in my opinion, useful up to the point that you stop learning definition from them. You know, if it's just an exercise in futile set theory, then, sorry, futile. Wait a minute, is it futile or is it futile? It's a futile question. Wait a minute, no, is it? I don't know, but shut up. All right, so here's what I'm more interested in. Example 3.64. So consider the map. So we're actually going to be able to go back to some, like I'm hopeful today that we get to the point of establishing some of the homeomorphisms that I talked about last class, but I'm probably wishful thinking. I think I'm still several pages from it. Homeomorphisms. So Rn plus 1 without the origin, right, to S to the n sphere. We can define by Q of X equal to X divided by the length of X, all right? That's well defined because we're not feeding it the origin, right? He says, observe Q is continuous and surjective. I believe it, right? Do you believe it? Any point on Sn we can obtain from Q. I think that's reasonable. It's continuous, it's surjective, and what are the fibers of Q? Like here, let me do S1. Yeah?
Can I guess without thinking about it very hard?
Sure.
Lines shooting up from the origin?
Correct. I think that's right. I think there are lines through the origin. Of course, without the origin.
Yeah.
Right? So if we take, if we look at n equals to 1, right? We've got the unit circle, right? And like what's the inverse image of a point on the unit circle under this map? I don't think it's lines through the origin, actually. I think this one is rays.
Yeah.
It's rays. So, like, that's the inverse image of that point. You know? And so the fibers are literally just the rays from the origin. Yeah. And so he says the saturated sets then are unions of open rays. And he says it's easy to check that Q takes saturated open sets to open sets and is therefore a quotient map. So if you have, so the question is, what's an open set on the circle, right? So we usually define that by the so-called subspace topology. So like, to define what's open on the circle in terms of the standard subspace topology inherited from the plane, if you take an open set in the plane, it looks like this, right? So open sets on the circle are like these kinds of things. All right, like you can't get a singleton because you can't touch just one point, right? You always have to at least get some. It's like here's an open set in the plane. This is the part of the circle which intersects with it. So essentially, open subsets of the circle are formed from unions of curved line segments. You could think of it that way.
And those map to wedges.
Right, yeah, and so the inverse image of these under the quotient map is a saturated set. I mean, it's, so that, if we look at a union of fibers, right, sorry, I think what you said was good. Thus, the saturated sets are unions of open rays, and it's easy to check that Q takes saturated open sets to open sets. So a saturated open set is a union of fibers, which is also an open set, right? I can't just take 3 of these. That would be saturated, right? But if they weren't the same, well, I mean, if there's 3 of them, then they're separated. That's not an open set, because like an open subset of the plane, again, every point in it has to be interior in the sense that you can put a little open disk around it, So if I take a bundle of them that are, filling out some wedge, then that's an open set. I'm running out of words. A wedge, yeah. Okay. Next example, the cone Oh, thank you. So example 3.65, if we look at the cone of topological space X, right? And I guess we should probably remind ourselves what that was, right? Come on. So so that was X cross I mod X cross the 0, right? This is the cone of X. And this is the place where we had some, we think there's a typo there, right? And there's an example which comes back to that. I think we can settle that today if I get to it. No. We'll settle that today because I'm going to get to it. You state that, yes. So, example 3165, he says the set X, Cartesian product, the singleton 1, is saturated, closed subset of X cross I. Now remember here, I is what? It's the unit interval, okay? Don't think of that abstractly. That's just the unit interval, right? So does that ring true to you guys? What is the quotient map here? Let me write it out. Q goes from where? from x cross the unit interval to what? To cx, right? Is that right? I think so. He says x cross 1 is a... I'm trying to remember what the... oh, goodness gracious. What was the equivalence there? Oh. So that gets squished. This is what gets... anything in that set is equivalent to anything else in that set, right? All right. So he says, anyway, this is a saturated closed subset of x cross I. So the quotient map, I got it right. I guess I should just read the next sentence, right? So the quotient map here, it restricts to a quotient map from x cross the singleton onto its image. All right. And he calls this x star, I think. Right. He says the composite map Huh? Oh, yeah. This. I know. All right, so then he's like, if we look at x is identified with, I mean, this is kind of dumb. If we take x and identify it with x Cartesian product to singleton, and that, of course, we can go over to x, that's this quotient map, right? I should give it a new name, you know? He says the composite map, which he hasn't actually written down, is an injective quotient map and is therefore a homeomorphism. He says one typically identifies x with its homeomorphic image, x star, a subset of cx. So basically you can think of x star as a subset of the cone over x. And it's this is a home. So anyway, the cone over x, long story short, is there's a canonical way of seeing the space x as a subset of the cone over x. And it's done using this identification paired with this quotient map. The reason this is a quotient map is because the set x Cartesian product with 1 is a saturated closed subset. Therefore, by the other theorem we have over there, if you restrict to a saturated closed subset, you get a quotient map. So example 3.66, I wish I could draw a picture of this. I don't have a good picture of the cone. Example 3.66. It's got some details in here. I think for the sake of I think I better get out the projector at this point. I think that I have to admit, you know, we made it this far. So, my apologies. But My topologies, yes. The mission is no, ambition, yeah. Well, we got started a little bit late today, but I can't necessarily go that late, so now the question is, can I actually find the scan, you know? So I have a very poor scan, sadly, of I have some much more nicely written notes on the quotient space, but they're from, I think, Minetti. And he starts with saturated sets, and I find it to be less understandable. I like that he's waited until the point of asking the question of, hey, is this map a quotient map, to start talking about the saturated quotient sets. I think if you really study John Lee's text carefully, you'll have a very, a pretty complete and healthy, what's the word? Oh man, did I not save it in there? Stink. Where did I put it? I mean, I know it's in Canvas, but I hate to go there. I guess I have to go there. Doot, doot, doot. I did put it in Canvas, right? This thing I've been lecturing from. I didn't print it out for you guys, did I?
You did not.
Okay, good. Because that means I must have posted it in Canvas. Otherwise, that would have just been a real jerk move. Of course, you could ask my linear algebra class. They might say, your point. Let's see here.
Did you like that test yesterday?
Some of them want to kill me now, I think. That seems to be my impression anyway.
Oh,
yeah,
Danny's
yeah.
girlfriend?
Daniel's girlfriend. That's beautiful.
Does she want to kill you?
At least Daniel.
Maybe
At
not.
least
Maybe not more than ever that I said that.
at least Daniel's girlfriend. Yes. All right. Finally, here we go. Here we go. Sorry. I wish I could. I'm an idiot. I should have got this silly thing out and projected through the part I wrote up, because the part I'm about to show you is the part I really wanted to write out. Oh well. I guess next time I teach advanced analysis, I'll do it right. There's, yeah, it's too late. It's not too late to apologize, but it's not too late to apologize. We still have like 20 minutes. So let's see here. So yeah, these are a selection from John Lee's book that I've been trying to work through. Again, it's his book on topological manifolds. And let's see here. So we got to right here. This was the next example. And so he considers a map from the identity to S1, again, the unit circle. Identity, listen to me, the unit interval to this unit to the circle, given by the exponential of 2 pi I times t, right? So it wraps around the circle at constant speed, yeah. And so he points out that it's continuous and it's surjective, and then this all shows that it's a quotient map, all right? So what he has to do is he shows U is open if and only if the inverse image under omega of U is open. So the if and only if's got two parts. First of all, the inverse image under U is open because it's continuous, great. Conversely, suppose that this is open.